Hello, I'm John Daly, CEO of Myers Emergency Power. As you know, the lighting industry is going through a major transformation with LED products, and that is increasing the popularity of lighting inverters. Many of the solutions that we're going to talk about today are because of the LED transformation. While inverters are becoming the preferred choice for many contractors, engineers, designers, etc., we still get calls every single day from people asking about how and where they can use inverters on their projects. Since we get so many calls, we thought it might make sense to hold an informative webinar to try to address some of the myths about inverters, as well as addressing some questions that we get on a daily basis. Apparently, there was interest in our idea, as there are well over 500 people watching the webinar, including engineers, architects, contractors, lighting designers, and industry salespeople. At the end of the presentation, we would like to get your feedback on what you would like to see addressed in future webinars, as well as asking any questions that you might have. The questions and responses that we get will be compiled and sent out to each of our attendees via email. So thank you for joining us today, and we look forward to your feedback. Now let me turn our presentation over to Conrad Pasil, who's the head of our engineering department, and he's going to walk you through some of the myths and basics of lighting inverters. Thank you.
Starting with an overview, this training is split into two segments. The first segment will provide a basic understanding of emergency lighting solutions, different types, inverter systems, and applicable codes. The second segment will focus on common misconceptions about inverters. So if you currently do not use, specify, or understand inverters, this training will help convince you of the significant benefits that inverters have over the other emergency lighting solutions. If you have any questions during or thoughts after this webinar, please forward them to info@myerseps.com, as we will be compiling a list and sending out. Anytime you're discussing emergency lighting, it always starts with the codes. A whole seminar can be dedicated to emergency lighting rules and regulations, but I will highlight some of the major codes from manufacturing to maintenance. The first two, UL 924 and UL 1008, are manufacturing standards that are in place to ensure the equipment will automatically supply the intended illumination in the event of a failure with the electrical supply. UL 924 regulations mainly cover the backup power source, and U1008 regulations govern transfer switches and equipment that typically transfers power from a normal power source and emergency power source. The NEC or NFPA 70 codes govern the safety of the installation, operation, and maintenance of the emergency power systems, as well as optional standby systems. There are three subsections, Article 700, 701, and 702, that contain the bulk of the regulations on emergency power systems. NFPA 101 and NFPA 111 regulate the performance, installation, test, and maintenance. These codes govern the complete safety system inclusive of site requirements. Some examples are the runtime, illumination levels, average and minimum, ratio of light to dark along the path, record keeping. The codes listed above have an overlap in requirements, and also there are various solutions to provide emergency lighting. So at times it becomes quite challenging for anyone to understand the exact intent. In an effort to make it crystal clear, the AHJ, or authority having jurisdiction, is assigned to interpret the codes above, as well as all of the local and state codes. The next slide covers two different types of emergency lighting solutions. There are two different classifications and two products within each classification. The first classification is decentralized solution that consists of unit equipment, commonly referred to bug eyes, and integral or remote battery packs. Unit equipment is installed along the path of egress as shown in the diagram and normally is powered off. When the utility power fails, it's powered from a small self-contained battery. Integral battery packs are installed in the fixtures and provide a portion of the full light output to illuminate the path of egress. The second classification are centralized solution that consists of inverters and generators. The term central is defined as a local power source serving a number of fixtures. Inverters can be located just about anywhere inside or outside the building: control rooms, closets, basements, ceilings, mezzanines. Typically, the smaller sized inverters are located near the served loads, and larger systems are located in dedicated power rooms. The power source for emergency operation is batteries. Generators are located outside the building with power sources for emergency operation coming from diesel, gas, or biofuel. Within the inverter category, there are two topologies: online double conversion and offline fast transfer. Double conversion systems have two independent power sections, an AC to DC converter and a DC to AC inverter, as shown in the diagram. Since the DC to AC inverter is actively powering the load all of the time, there is no transfer time when utility power fails, and it's fairly robust of areas with unstable power grids, such as third world countries. The disadvantage of the double conversion topology is poor efficiency because of the two conversion processes, higher cost, more opportunity for failure with increased parts and complexity, and also high harmonic ripple current in the battery bank, which reduce the lifetime of the battery. Offline fast transfer systems have one power section that is used to charge the battery bank and supply the load during emergency. Offline fast transfer systems are the preferred choice for emergency lighting due to minimum transfer time, 2 to 10 milliseconds, which is well acceptable for lighting systems, minimum harmonic content, very high efficiency, and lower cost. The next couple of slides will illustrate the wiring and operation of a fast transfer inverter system from the utility source through to the load. During normal operation, the backfeed switch is closed, allowing power to feed directly to the load, as well as the AC to DC converter, which is keeping the batteries float charged. The non-egress areas have standard wiring and operate as a normal lighting circuit. On the lower right side, there's a shunt relay which performs three functions. First, it provides a mechanism of control for the light switch to turn on and off the egress lights. Secondly, it monitors the unswitched hot to determine when the incoming utility has been lost. And third, with the loss of power, it provides a bypass line for emergency power to feed the loads when the utility has failed. During emergency operation, the utility company main power feed is lost, illustrated by the gray color in the diagram. Instantaneously, the backfeed switch opens, disconnecting the utility company from the inverter system, so no voltage is fed through to the utility grid. The power module reverses from an AC to DC converter to a DC to AC inverter. And the shunt relay closes passing emergency power to the load, independent of the room lighting control. Summarizing the advantages and disadvantages of the different types of emergency lighting solutions, starting with the unit equipment, on the plus side, very low cost, simple to wire, readily available, and easy to identify the emergency fixtures. Disadvantages are objectionable to most people in spaces, costlier to maintain, testing and logging, If it has auto test self-diagnostic units, there's a higher per fixture added cost, and it's a poor outdoor solution. Integral battery packs have advantages of low cost, visually unobtrusive, only the light and test switch are seen through the ceiling, and short to medium lead time. Disadvantages are it does not provide full output, so more fixtures are required for emergency. It's not available in all lighting fixtures. It can only be used to power lighting. It requires an additional unswitched AC wiring for sensing. Testing and logging are non-automatic and costlier. It's costly to replace the batteries, and it's a poor outdoor solution. Generators' advantages are the interior is visually the same. Power any loads that can accept seconds of interruption. Powers both indoor and outdoor loads and has fairly simple wiring. Disadvantages include high initial unit cost and installation. The transfer time is in seconds. They typically come in larger capacities. If generator serves both emergency and non-emergency loads, a separate transfer switch and emergency panel is required. There is significant engine maintenance. It requires a large outdoor mounting space, noisy, unsightly, and environmentally unfriendly, and generally have longer lead times. Inverters have advantages of the interior is visually unchanged. The system is a fast transfer. There's no cost for testing or record keeping. There's a single area for battery replacement. Full light output for the entire 90 minutes. It can power any type of lighting and also more than just lighting. Suitable for indoor and outdoor lighting. Simple to install and quick lead times. The main disadvantages come from a lack of education and misperception. Another disadvantage for the larger systems is the space required. But you can always use multiple small units, wall, ceiling, or in closets or beam mounted to occupy smaller spaces. One of the greatest assets of the inverter system is the simple diagnostic that's offered, monitoring, testing, and historical records in the form of alarm and test logs. The NFPA compliant automatic testing and logging feature stores the results from 2 years of monthly and yearly tests internally in a non-volatile, easy viewed for the local inspector. This data can also be made available via communication systems such as BACnet to the BMS system. Emergency lighting is used in every application where the public is involved. Obvious applications include healthcare, schools, commercial buildings, public transportation, hotels, and churches. More recently, due to code changes expanding the path of egress, installation of safe rooms, redundancy requirements, and applications that require minimal transfer time, new areas have risen such as city parks, common walkways, assisted living centers, safe rooms, prisons, and tunnels. Due to the increased number of applications using LEDs, a reduction in power requirement occurs. This LED technology drove a trend on both ends of the power spectrum. Large applications that may have been too large for an emergency inverter now will fit in an inverter, and small applications drove the need for micro and mini inverters. The traditional large central systems are used on applications from 2 to 50 kVA, installed in electrical rooms. The mini category from 100 VA to 2 kVA are typically installed in closets, wall-mounted ceiling grids, and on roof beams. The micro application, less than 100 VA, typically mounted near the fixture in the ceiling. Some of the application requirements drive product choices that must be specified at the time of order. Some of the choices are application specific, and other may be value-added options that absorb products that are typically installed outside of the inverter system. Inverter output types include normally on, which are loads that are powered in both non-emergency and emergency situations, such as exit signs. Switched loads, they're controlled by switches during normal operation and forced on emergency, dusk to dawn lighting, standard room lights. And normally off loads, they're only powered during emergency operation, such as floodlights or pathway lighting. Single-phase inverters are more commonly used for cost reasons, but some applications require three-phase motors, or if the current is large enough, lowering the wire gauge may make sense to use a three-phase system. Other useful options include communication options connecting to BMS systems, output distribution, trip alarms for detection of disconnected emergency loads, remote testing capability, maintenance bypass for service, factory startup, and extended warranties. One of the points that was touched on earlier was NFPA 101, defining the path of egress requires emergency lighting to illuminate to the public way. The definition of the public way is a street or alley open to the outside, air-deeded, dedicated, or otherwise appropriated to the public for public use, having clear width and height of not less than 10 feet. This is a long-winded statement that says the illumination must extend away from the building to a safe area. This created a need for outdoor NEMA 3R systems with unique requirements due to temperatures, precipitation, debris, bugs, etc. Outdoor inverter systems have superior performance when compared to unit equipment or battery packs that would be placed in this harsh environment. Small power units are pole-mounted or pad-mounted and range from 875 VA single-phase to larger 10 kVA three-phase systems. Outdoor inverters are compatible with all outdoor fixture types, including integral or remote photocells. Now would we like to move on to some of the myths that occur within inverter systems. So the first myth is inverters are only for big jobs. In previous discussions, we talked about the reduction in power with the advent of the LED. Typically, the power required is between 10% and 25% when a changeover to LED occurs. In this example, typical loads would have generally consisted of TA troughers, CFL downlights, and incandescent lights that total 1,876 watts. Looking over to the LED case, the same design replacing the troughers, downlights, and pendants with LEDs would reduce the power to just over 500 watts. Extending this example to larger and smaller systems, a 200 kilowatt system with older lighting technology would require a 50 kilowatt system today, and a 200 watt system of yesterday would require a 50 watt inverter today. The takeaway is that lighting loads are lower power today, and for every application, there are inverters available with power capacities that meet the requirements. Inverters are too expensive. In performing a cost analysis, all aspects within the life of the system must be taken into consideration. For many years, our message was always that inverters may not be the lowest cost up front, but they were the correct choice when analyzing total cost of ownership. With LEDs, that dynamic has changed, and this example will illustrate why. Starting with the first cost. In this example, we considered a layout with 22 EM fixtures. The cost in labor at $60 per hour to install the battery packs into the fixtures would be $4,730. On the inverter side, for the same space, a 175-watt system would be required, and the assumption is that there are 5 different switch zones in this space, which would be a worst-case scenario. The initial cost of this inverter system is $2,290, which is less than 1/3 of the battery pack solution. Now that the system is installed, it must be maintained through the required compliance testing. For integral battery packs, a test time of 2 minutes was assessed per fixture per month, and 90 minutes for all 22 fixtures once per year. At $60 per hour labor rate, the total compliance testing for 15 years is $85.80. The inverter already has the code-compliant monthly test and yearly tests performed automatically. The final piece of the puzzle is the replacement cost. The batteries for the battery packs are changed every 5 years, so there are 2 change-out of batteries and the life cycle cost of $57.20. The inverter batteries are changed once, and a few electronic components, the total cost of $25.89 over the 15-year period. In summary, the inverter system is the initial lowest cost solution from the start, and the total cost of ownership is about 25% of the integral battery pack, or a 75% savings. The next myth is inverters are too complicated and costly to wire. This example walks through a wiring scenario of an integral battery pack compared to an inverter system. With the integral battery pack, the main wiring from the meter to the sub-panel is identical to a standard building installation. An extra wire is required to each fixture for the sensing of the utility line. In the case of inverter, downstream of the sub-panel, you have the input and output wiring to and from the inverter. A shunt relay is placed in each zone that the emergency circuit is wired through, and the switched-unswitched hot connects to the shunt relay as well. The shunt relay provides the sensing and control for the power to the emergency lights. The output of the relay contains the emergency wiring that powers the fixtures. In summary, the inverter system only requires an extra hot and neutral. The next myth was inverters are not good for retrofit or remodel jobs. Since not all spaces are new construction, retrofit applications are a great fit with inverters. LED retrofits reduce the load requirements of the application. Micro and mini inverter come in a variety of power sizes and mounting configurations, providing maximum flexibility for the application. Built-in control features like switch circuits and dimming controls simplify the wiring and can be tied directly into the J-box. Worst case scenario, a constant hot wire is required to be added in the J-box. Takeaway is that an inverter is the best choice for a retrofit, cleaning up the aesthetics in the space and capturing the maintenance savings as explained in an earlier myth. Inverters are too large for most applications. In the past 5 to 10 years, LED power requirements dropped, as well as inverter power sizes. For applications up to 3 kilowatt, most inverters are wall-mounted versus cabinet structures and occupy a much smaller wall or footprint. Microinverters, which are less than 100 watts, have superior mounting flexibility and can be mounted in plenums, ceilings, and on walls. Summary is that there's a variety of sizes of small inverters available to choose from, so the same space can have one or multiple inverters accommodating the emergency lighting needs, as well as the space that's available. The next myth is I do not need an inverter for projects with a generator. There are many applications where the longer transfer time for a generator may be undesirable or even compromise public safety in certain applications. NFPA 111 refers to an emergency power system type designation to describe the transfer time, and generators fall in the type 10 class, which inverters are a type U class. Critical applications that require type U were traditionally HID lights, which would have a long restrike time. More recently, applications such as surgical suites, prisons, 911 call centers, stairwells, which have an outage of seconds that can result in an undesirable effect. So the takeaway from this slide is that inverters can work alongside generators for applications where the long transfer time or sensitive areas that require redundancy. The next myth is inverter battery maintenance is too difficult and costly. Inverters perform routine monthly and annual self-tests that are governed by NFPA 101 and can interface to fire alarm panels, BMS systems, or other monitoring systems. The battery used in central systems are superior quality to other emergency systems. The charging algorithm, minimal ripple current in the battery string, and the automatic testing exercise the battery, extending its life. The battery's maintenance and replacement for central lighting inverters is much easier than other technologies. Factory or factory-trained service centers can perform the needed maintenance at intervals of your choice. Load testing, cleaning, inspection, replacement, and disposal are all services that can be provided. If you have your own maintenance staff, then factory training is available so your staff can maintain the battery system. Takeaway from this slide is that battery maintenance is minimal, cost-effective, and there are maintenance programs available that can suit any customer need, including training your own staff to perform the routine maintenance. Inverters do not work with lighting controls. For the smaller inverter systems, the basic controls that would be traditionally built outside of the inverter system can be included as options. These include shunt relays, switch circuits, 0 to 10 dimming controls, and controls to third-party systems. For larger systems, shunt relay and transfer switches tie into the inverter system, providing the local controls required so that a subset of the normal lights can also function as the emergency light with minimal additional effort. The final myth is I can use an inverter in an area having seismic requirements. There are two versions of seismic ratings available, which are classified as standard seismic and OSHPOD seismic. Standard seismic ratings are calculations performed by a certified engineering firm on bracing, mounting pad, and mounting brackets, ensuring that the inverter will not fall over in the event of an earthquake. OSHPOD seismic ratings are certifications performed at a laboratory by mounting the entire unit, including batteries, on a steel deck and shaken in the X, Y, and Z planes to a specific level, which is determined by the target zone in the county and the height that the equipment will be located. The equipment must survive the test and be fully functional after the test. Summary is that the Myers EPS inverters have been tested to the most stringent seismic levels, allowing to be put in any location in the U.S. This training was an overview of emergency lighting codes, types, applications, and additional details on fast transfer emergency lighting inverters. Please forward any questions to the email shown, and we will compile a Q&A document as well as this presentation via email sent to the attendees. We will be performing these webinars from time to time, so feedback on the content, areas that require more detail, or new subject topics would be greatly appreciated. There are 3 different ways to get in touch with Myers EPS. Through your local sales representative, which you can locate from our website. Click on How to Buy, find a sales rep, Emergency Lighting Power Solutions, and select your state. Through one of our outside sales managers, or Myers EPS directly. We have a great application engineering team that knows our products as well as the applications that they serve to ensure the end customer will get the right product for the right application. This is a great asset that sets Myers EPS apart, so please take advantage of the resource. Myers would like to thank you for attending the webinar and hope it was informative for everyone. And please submit your questions and concerns and we'll address them. Thank you.
No, I was going to go back to the slide with the question email. Great. All right, thanks everybody. We look forward to hearing your feedback, and hopefully we'll see you in a future webinar very soon.